Imagine three people opening the same news story about a new artificial intelligence data center. An illustrator sees a machine that may have learned from years of work posted online without permission. A grid operator sees hundreds of megawatts of new demand arriving faster than transmission lines can be built. A nearby resident sees cooling towers and wonders what will happen to the local water supply. None of those concerns is imaginary. But now imagine the story spreading online. Soon, every image model is described as a database of stolen pictures. Every chatbot question consumes a bottle of water. AI is said to be using more electricity than entire nations, as though that comparison ends the discussion. Those claims contain pieces of truth, but the pieces are often assembled into the wrong picture. There are two easy positions in this debate. One says AI is weightless software, so its harms are mostly panic. The other says AI is uniquely extractive, so any benefit is merely an excuse. Neither position survives contact with the measurements. Today, we are going to follow the numbers through two of the most serious criticisms of generative AI: the use of creative work in training and the electricity and water consumed by data centers. The goal is not to declare AI innocent. It is to separate mechanism from metaphor, global scale from local impact, and solvable engineering problems from real questions about rights and power. Because being optimistic about AI should not require pretending it is free. It should mean believing we can build something valuable enough and govern it well enough to justify its costs. This is AutoIntellect, practical intelligence grounded in the physical world. Let us begin with the most common image model myth, that the model is a giant compressed folder of other people's art, cutting up stored pictures and pasting the pieces together. That is not how modern diffusion models normally work. During training, software repeatedly shows a model images paired with words. It adds noise, asks the model to predict what was obscured, measures the error, and adjusts billions of numerical parameters. Over many examples, those parameters become useful for representing visual relationships. What fur tends to look like, how light wraps around a face, or how the word watercolor relates to edges, pigment, and paper. When the finished system generates a new image, it usually begins with noise and iteratively constructs a result. It is not normally retrieving one source image from a hidden gallery. But the model is not a collage engine, does not settle the ethical question. Training still requires access to actual files. Web-scale datasets have pointed to billions of images, including copyrighted illustrations, stock photographs, and personal pictures. Leon, one influential open dataset, distributes links and metadata rather than the image files themselves, but a developer training from it must retrieve images from those links. Saying the final weights are not a photo archive does not erase the copying and data collection that happened upstream. Models can also memorize. In a 2023 study, researchers used a deliberate generate and filter attack to extract more than 1,000 examples from several diffusion models. Memorization was not the ordinary behavior of every prompt, and repeated images were especially vulnerable. But the result disproved the absolute claim that training examples can never come back out. So, the accurate sentence has two halves. A generative model usually learns statistical structure rather than storing a searchable library, and poorly curated or overtrained systems can still reproduce protected or private material. Both facts matter. The next myth is that there must already be one simple legal answer. Either all training is theft or all training is fair use. In the United States, there is no such universal rule. Fair use is a case-by-case test involving purpose, the kind and amount of work copied, and effects on the market. The U.S. Copyright Office concluded that some uses of copyrighted work for generative AI training will qualify and some will not. Two federal trial judges ruled in 2025 that the training uses before them were fair use. But one of those cases involving Anthropic drew a sharp boundary between training and acquisition. The judge found training transformative, yet held that building a permanent library from pirated books was not justified by that training purpose. In July 2026, a court approved a $1.5 billion settlement covering those pirated copies. That settlement did not turn the earlier training ruling into infringement. It demonstrated that how data is obtained can matter separately from what a model later learns. Visual art cases, output similarity, licensing markets, and appeals can produce different answers. Style by itself is generally not the same thing as a copyrighted work, but a near copy may infringe, and a flood of cheap imitation can still damage a creator even when no single output crosses that legal line. Ethics, economics, and copyright overlap. They are not identical. The mitigation path is already visible. Adobe says its Firefly models use licensed and public domain material and that eligible stock contributors are compensated. The research project Common Canvas assembled roughly 70 million Creative Commons images and produced a model competitive with an earlier stable diffusion system using far less data. These examples do not resolve every license term or compensation dispute. They do show that indiscriminate scraping is a business choice, not a law of machine learning. Better systems can publish dataset summaries, record licenses, honor machine-readable rights reservations, remove duplicates before training, test for memorization, block near-duplicate outputs, and offer accessible removal and dispute processes. The European Union now requires providers of general-purpose models to publish a training content summary and maintain a copyright policy. Content credentials can attach tamper-evident provenance to human and AI-assisted media. The long-term bargain should be straightforward. More transparent inputs, better choices for creators, real licensing where it is practical, and useful creative tools that expand what people can make. Now walk from the dataset into the data center. The International Energy Agency estimates that all data centers used about 415 terawatt-hours of electricity in 2024, roughly 1.5% of global electricity consumption. That includes ordinary cloud computing, storage, streaming infrastructure, business servers, and AI. It is not an AI-only number. 1.5% is significant. It is also not an energy takeover. For perspective, space cooling accounts for roughly 10% of global electricity demand, several times the entire data center share. Buildings use around 30% of total global energy. We already operate physical systems much larger than data centers without concluding that their benefits are impossible to justify. But the direction of travel matters. The IEA projects data center electricity use to reach about 945 terawatt-hours in 2030, just under 3% of global electricity. AI-accelerated servers are expected to produce nearly half of the increase. Data centers are growing much faster than electricity demand overall. There is another useful denominator. Between 2024 and 2030, data centers are projected to account for less than 10% of the growth in global electricity demand. Industry, air conditioning, electric vehicles, and broader electrification collectively add much more. This is the honest middle. AI infrastructure is a fast-growing industrial load, not an ecological rounding error, and not the dominant use of world electricity. The world can supply it. The important questions are what generation gets built, who pays for the grid, and whether the computation is worth doing. Global percentages can hide local stress. In the United States, data centers consumed an estimated 176 terawatt-hours in 2023, or 4.4% of national electricity. A Lawrence Berkeley National Laboratory analysis projected a wide 2028 range, 325 to 580 terawatt-hours, or 6.7 to 12%. That uncertainty is important. Forecasts depend on how many accelerators are shipped, how heavily they run, how efficient the hardware and cooling become, and whether announced facilities are actually built. The load is also clustered. A data center is not a thin layer spread evenly across a continent. It can arrive as a factory-sized demand on one substation in one utility territory beside one community. New gas plants, transmission lines, backup generators, and electricity rate changes are local events, even when the global percentage looks small. This is why the popular energy per prompt statistic can mislead. A company measurement published by Google estimated that the median text prompt in its Gemini application used 0.24 watt-hours and about 0.26 milliliters of water, roughly 5 drops. That is evidence against the idea that every short chatbot exchange consumes a bottle of water. It is not a universal constant. A long reasoning task, a high-resolution image, or generated video can require far more computation. Providers use different models, chips, utilization rates, cooling systems, and power grids. Even a tiny unit multiplied by billions of requests becomes infrastructure. The right lesson is not that prompts are free or shameful. It is that providers should publish measurements with clear system boundaries, and users should choose the smallest model and shortest computation that reliably does the job. Water produces the most vivid claims and some of the worst comparisons. Data centers may consume water directly by evaporating it to remove heat. They also have an indirect water footprint because many power plants consume water while generating electricity. Withdrawal means water taken from a source, often returned later. Consumption means water removed from the immediate cycle, commonly through evaporation. Mixing those terms can change a comparison by orders of magnitude. Berkeley Lab estimated that U.S. data centers directly consumed 66 billion liters of water in 2023, about 17 billion gallons. Their electricity was associated with an additional indirect footprint of nearly 800 billion liters, based on the regional grid mix. Those are large volumes. Here is the national context. The U.S. Geological Survey estimated that irrigation consumed about 73 billion gallons of water every day in 2015. Using these national figures from different years only as an order of magnitude comparison, spread the direct data center number across a year and it becomes about 48 million gallons a day versus 73 billion, roughly 0.07%. Include the estimated power plant footprint and the comparison remains under 1%. Nationally, data center water is not close to agriculture's scale. Locally, that may be the wrong comparison. A liter consumed in a wet region during winter is not equivalent to a liter taken from a stressed aquifer during a summer heat wave. A facility competing with households and farms in one watershed cannot point to a national pie chart and declare the problem solved. Water impact is geography plus timing plus cooling design, not a magical number attached to every prompt. None of these resource costs is fixed. At the model level, developers can route simple requests to smaller models, quantize weights, reuse cached results, batch compatible work, limit wasteful retries, and report energy per completed task rather than celebrating model size. MLPerf results show that performance per watt can improve dramatically across generations of hardware and software. In the IEA's high-efficiency case, stronger progress across chips, software, and infrastructure reduces 2035 data center electricity demand by more than 15% while delivering the same digital services. At the facility level, operators can schedule flexible training when clean electricity is abundant, participate in demand response, and build new generation and storage instead of merely claiming the output of existing clean plants. Utilities can require realistic interconnection deposits, long-term power commitments, grid upgrade contributions, and protections that keep ordinary customers from underwriting speculative capacity. Water strategy should be site-specific. Options include reclaimed water, closed-loop liquid systems, airside economizers, warmer operating temperatures, and dry cooling where the extra electricity is an acceptable trade. A dry system may save water at the facility, but consume more power and shift water use to a power plant, which is why energy and water must be modeled together. Nearly all electricity entering a server becomes heat. Berkeley Lab estimates that roughly 70 to 80% could technically be recoverable. Near a district heating network, greenhouse, or industrial user, some of that waste can become a product. In an isolated campus with no nearby customer, recovery equipment may accomplish very little. Good mitigation is concrete: a cleaner grid connection, a less stressed watershed, an efficient model, a flexible load, a useful heat customer, and public reporting that lets the community verify the claims. There is one final myth worth discarding: that AI's footprint and AI's climate value cancel each other automatically. They do not. A model that writes advertising copy does not become carbon neutral because a different model improved a wind forecast. But the upside is real. The International Energy Agency evaluated existing AI applications in buildings, industry, transport, and energy systems. Under widespread adoption, it estimated potential emissions reductions of about 1.4 billion tons of carbon dioxide in 2035, around 5% of energy-related emissions, and several times the projected emissions from data centers themselves. The examples are practical. Better heating and cooling control can reduce a building's energy use. Route and driving optimization can cut vehicle energy consumption. Computer vision can find industrial defects before they become waste. Forecasting can help grids integrate variable wind and solar. Models can search material candidates for batteries, catalysts, and lower carbon cement. Those gains are not guaranteed. Equipment must be installed, operators must trust it, and efficiency savings can be swallowed by rebound, when a cheaper service is simply used more. AI is a lever, not a climate policy. The same is true in creative work. Generative tools can lower the cost of storyboarding, restoration, translation, accessibility, and experimentation. They can help a small studio attempt work that once required a much larger budget. But that future is stronger when the people whose work helped build the tools can inspect the bargain, object where appropriate, and share in the new market. AI can help solve problems larger than its own footprint. That possibility is a reason to deploy it deliberately, not a permit to ignore its costs. So when the next alarming AI statistic appears, ask 4 questions. What exactly is being measured? One model, all AI, or every data center? Compared with what? And are the units, years, and system boundaries the same? Where and when does the impact occur? And who receives the benefit, bears the cost, and has the power to say no? These questions do not make criticism disappear, they make it useful. The art concern is not best described as a machine secretly holding every painting it has seen. It is a question of lawful acquisition, consent, compensation, transparency, memorization, and market power. The environmental concern is not best described by assigning one universal bottle of water to a prompt. It is a question of rapidly growing electricity demand, particular grids and watersheds, hardware efficiency, generation mix, and whether the work creates enough value. A serious pro-AI position should welcome those distinctions. It should demand licensed and well-documented data where feasible, measurable efficiency, additional clean power, responsible siting, honest community agreements, and models matched to the task. That version of AI may cost more to build than one based on invisible inputs and externalized infrastructure. It will also be more durable, more trusted, and more useful. The experiment for this week is simple. Pick one AI tool you use and inspect its model card, data policy, or environmental report. Look for what is measured and what is missing. Then try the same task with a smaller model, a local model, or a tool trained on licensed material. Optimism is not the belief that technology has no cost. It is the belief that we can see the cost clearly, reduce it intelligently, and build something worth having on the other side. This has been AutoIntellect, practical intelligence grounded in the physical world.